Now, let's talk about linear transformations. By now, these concepts should be familiar to you because the linear transformations are transformations that we apply to any basic function. In this case, our basic function is a base, a number, positive number, raised to the power of x. If I apply any of these transformations, I'm modifying the structure of a function in a way that we are already familiar with. Remember that if you have a number that's adding or subtracting to the argument of the function, remember the argument of a function is always the place where the x or the variable resides. So if that you have a number affecting it by either subtracting or adding to the x component, that means an horizontal movement of the entire graph. If you have an independent term isolated on the outside of your function, that is a vertical movement. And lastly, you always have a leading coefficient, and remember that this modifies the rise or how fast your function grows. To remember this, let's look at this example. If I write this function like this, things start to look familiar. From this is an a. From looking at this, you can already tell that this function has a different vertex. The vertex of this quadratic function is not c, d. Is not 0, 0, but c, d. Meaning that this function had a horizontal shift because this has changed the vertex horizontally, and a vertical shift or vertical movement because this has moved the y coordinate, meaning a vertical movement. And lastly, you remember that a modifies the rise when we are applying the run rise method, or it changes the height of our function. Those same movements apply to exponential functions. So the important point, or the vertex, or the origin, every type of function we have learned so far has a really special point. For example, for quadratic functions, the starting point or the vertex was always 0, 0. For radicals, it was always 0, 0. Absolute values, 0, 0. Rational functions, 0, 0. So in this case, this is not different. We're always going to start everything from the origin, from 0, 0. And as we've seen here in this quadratic function, the coefficient that adds or subtracts to the x variable is going to move my starting point or my vertex or my origin horizontally and the d coordinate vertically. So let's start looking examples. In this example, first example, I have in green the function 2 to the power of x, and then I have in red the transformed function 2x plus 1. Notice that this is an independent term adding to the function. And by making an analogy with what we know, this means that if this was the origin, this transformation is going to give me a new origin from where I'm going to start evaluating everything. So my new origin is 0, 1. Why? Because we know that when we transformed or obtained a vertex, we would always get the independent term as the y coordinate of the new origin or vertex, however you want to call it. And to find the x coordinate for that new origin, you would always grab the argument of the function, equate it to 0, and solve for x. That's how you obtain the vertex of a quadratic, and that's how you will find the origin for an exponential function. So this means that this is my new origin. And also remember that the horizontal asymptote always passes through that new origin, meaning that my horizontal asymptote is going to be y equals 1, and it's going to pass through here. Now, from here, we're going to apply the important points of an exponential function. You know that any exponential function evaluated in 0 is 1. So this means that if I run 0, I'm going to raise the leading coefficient times the base to the power of 0. This means if I run nothing from my new origin, If I run nothing, I'm going to rise as always the leading coefficient times my base raised to the power of 0. In this case, my leading coefficient is 1 because I have nothing multiplying the two. And we know that b to the power of 0 is 1. So if I run 0, I'm going to rise 1. That is, starting from my new origin. If I don't move, I'm going to rise 1. Then if I run 1, this means that I'm going to rise my leading coefficient that we already said is 1 times b to the power of 1. In this case, my base is 2. So this is 2 to the power of 1, meaning 2. So if I run 1 to the right, I'm going to rise 1, 2. And that is how I know how to graph functions. So remember, in this case, we have to first identify the new origin and the horizontal asymptote, and then apply the run-rise method using the important points running 0 and running 1. Second example. Here I have a linear transformation in my argument, meaning that my function is going to have an horizontal displacement. How do I know that? I graph my argument, equate it to 0, solve for x, and I know that is the x coordinate for my new origin. Notice I don't have any independent term adding nor subtracting. That means that the origin's y coordinate is, as usual, 0. So this is my new origin. From there, I'm going to apply my run-rise method. So remember, my important points are 0 and 1. Those are the easiest ones to evaluate. So if I run 0, I'm going to rise a times b to the power of 0. My leading coefficient again is here, 1. Why? Because I don't have any number multiplying my base 2 to the power of x. So this is 1 times my base, that is 2, raised to the power of 0. And this is 1 times 1, this is 1. So starting from my origin, if I don't move, or if I move 0, I'm going to rise 1. If I rise 1, that means I'm gonna rise my leading coefficient 1 times 2 to the power of my run. This is 2. So if I run 1, I'm gonna rise 1, 2. And that's how I know where my function passes through. My third and last example here is a function that has both vertical and horizontal displacement. So first of all, I'm gonna find my new origin. Remember, the argument, if I equate my argument to 0 and solve for x, that is going to give me the x coordinate for my new origin. And if I grab the independent term, that is going to be the y coordinate for my new origin. So in this example, my new origin is 3, 1. Oh, remember to always sketch your horizontal asymptote. Thus, I'm going to start my run-rise method. And I know that if I run 0, this is my leading coefficient. In this case, again, I have no other leading coefficient but 1. So this is 1 times my base to the power of 0. This is 1. So if I don't run anything or I run 0, I'm going to rise 1. And if I run 1, I'm going to rise my leading coefficient times my base to the power of 1. In this case, my base is 2. So this is 2. So if I run 1, I'm going to rise 1, 2. So that is where my function passes through. And that is it for linear transformations with a just horizontal or vertical movement.